Hey everyone, so we're gonna just do another behind the scenes video. I went through most of the learning and understanding and thinking of the Graham Schmidt process. In the last video, went through all my logic, had that revelation about, you know, why that orthonormality even matters. At least I hope that's correct. I think that would make sense in higher dimensions. Um, I think the only real revelation thinking wise was just picturing this in 3 dimensions was something that was difficult for me. And like, I actually found this video earlier. I'm just going to show it to you, wherein someone does this in 3 dimensions and with 2 basis vectors already. So in this case, u prime over here and v prime over here are 2 different basis vectors, right? And then the projections or the sum of the projections is what gets you the new projection into this vector space over here. So that's what you see over here, this projection, and then this big ass card comes up. But the next part, which is getting the orthogonal value, which is w minus these two, then you just move that here to the orange to see that better. And then it doesn't do the next step of dividing this by the magnitude of itself to make it a new basis vector, but that was the only new learning thingy. So now we're just gonna jump straight to the code. Wait, what is this? Oh, it's the same video, same guy doing the same thing in 2 dimensions. Anyways, I don't need to go through that. I'm just gonna pause that video. I'm just gonna open up ChatGPT. It's over here. Just because I'm gonna refer to the math here as I'm working. I think I basically get it, but yeah. So from what I showed most of this code last time, these are all the different pieces of the things that we're gonna need. We're gonna need to sum up vectors. We're gonna need to subtract them from each other. We're gonna have to project them, which is just dot prod then scaled, right? Take the dot prod of u and v and then scale v by the dot prod, right? That's essentially what projection is. Scaling being multiplier times v, right? So you take the projection as the dot product of the previous basis vector with the current vector in question, and you scale the previous basis vector by this dot product. That's a projection, right? So I'd written out all the code pieces. I was honestly like, these were easy pieces for me to do, and I'm like, okay, let me just do these because I was tired and I really want to get through. I wrote this newly today, and I started working on the orthonorm just by myself. So get sum vec is literally getting the sum of a bunch of vectors. So I had vec sum, which specifically worked for 2, and then get sum vex is for just doing all of them, or doing multiple at a time, because to get the get the orthogonal vector, you need to take the vector in question and subtract it from the projections of all the previously calculated basis vectors with respect to the current vector, right? And subtract that from the current vector. That gives us the orthogonal thing. And then to normalize it, you have to divide it by the L2 norm. So as you can see over here, it's pretty straightforward. Now to just do that in code, I have a lot of the pieces together. Initially, I was thinking I had to actually keep track of the projections as well, because I saw this sum of projections, and in my head I was just like, oh, I have to do the sum of all the previous projections, right? Except no, you actually have to recalculate all the projections from scratch each time, because it's with respect to the current vector, right? So if you just look at the previous projections calculated, that doesn't make sense, right? Because that would be with respect to the previous vector, so that doesn't work, right? Um, so over here, I kind of did u0, so the first basis vector, and I did the second basis vector before going into this. Though I don't think I actually need to do this like this, but since I already, and then go into the loop from the second one onwards. So instead of doing that, I think I can change this so that the loop only does it starts from the first one and not from the sorry it starts from the second one or index one, because indices start at 0, so index 1 is actually the second element or the second vector, instead of starting from the third vector. But I just don't want to funk with this shui over here. Like, I don't want to screw up with what I've written so far, though technically I haven't tested it. I'm just gonna like, you know, do it in my just like take it from here, right? I do. So the first basis vector is exactly what I said: scale 1 over the L2 norm of this, and a 1 over the L2 norm of the first vector, and scale that with the actual vector itself, right? Or in other ways to put it, scale is just the name of my function and it just takes any multiplier, and in this case I gave the multiplier 1 over the L2 norm. But essentially what that means is I'm just dividing that vector by its magnitude to get the first basis vector. Then for the second basis vector, you're going to want to subtract that vector minus the projection of that vector onto the previous basis vector, right? And then you do the same thing again. You scale it with 1 over the L2 norm, etc., etc. Right? From here on out, though, we have to do all the projections. So I do for I in range 2 len LIV. LIV is linearly independent vectors. That's what I'm calling it. And I just create a list of all the projections, right? Then get some back P colon I. I think that's a holdover from when I was doing P separately and thinking I had to project it all, but I actually don't have to do that. I'm doing calculating these projections only for all the basis vectors up till now with respect to the current independent vector that we're looking at, right? Let me make sure I'm doing that correctly. Project UV. Oh, wait, maybe I'm doing this wrong. Okay, yeah, it should be actually scale dot product. Dot product UV is correct, and then scale U, not V, right? So I actually need to change that over here. I'm glad I caught myself on that. And I tend to do this thing a lot where I just kind of write all the code, a bunch of the code, because I'm like good at thinking about it. But if you're doing this at home from scratch, or if you're just starting, or if you're in the earlier things like you're doing Gaussian elimination or just plain old matrix multiplication or whatever, just make sure you keep doing like testing in between. It's really helpful. But also, if you've gotten good enough at thinking about it, at some point it's like, okay, I don't want to worry about like how do I test this and do a print statement so that I see it. I'm just gonna like write the code. That's also not a terrible approach, right? But it can become difficult to debug if you're not confident. And it's especially fine when you're playing around like this by yourself, but it's difficult if you're trying to work in a production environment and stuff like that. So I have this bad habit, basically don't pick it up, but also don't worry about it too much if you have picked it up. Okay, so let's just make sure this is correct. Take the current vector and subtract it from the sum of all the projections. Get some vec gets this. क्या हो गया आंटी, सब ठीक है? ले लो उधर से, होना तो चाहिए, कमरे में नहीं है? आंटी कैसे आप घुमा सकते हो एसी का रिमोट? लेके जाओ ये वाला। अरे कर क्या रहे हो? I'll be back, kids. कहाँ गया आपका एसी का रिमोट? है तो सही इधर, और आप लेके क्यों नहीं गए? दो रिमोट है हाँ, तो इधर का कहाँ है? चलो ये रख लो अभी जो भी है, मुझे अपना संडे हाँ मम्मी काम कर रहा हूँ, वीडियो रिकॉर्ड हो रहा है अभी, बताओ। Anyways, so that's what you get with behind the scenes. It's raw, and also I don't know how to edit. क्या हो गया आंटी? क्या हो गया? I don't know what happened. Anyways, right? So let's make sure the projections are right. So U is the basis vector, right? LIVI, that's the current vector I am looking to do the projections for. And I do that with respect to all the projections, all the basis vectors that we've calculated up to this point. Fair enough. This seems to make sense. I'm doing that correctly. It's project dot prod scale the basis vector based on this, right? Scale the basis vector. Yeah, U is the basis vector. Right? Yeah. So now what do we do next? And then we just do... Did I actually already finish this? I think I might have. UI equals scale 1 over L2 norm UI. Oh wait, what did I do here? UI. Yeah, that's correct. Right, I have to scale, I have to divide that by its magnitude to get the final answer. Well, I think this might be it. I think this video is going to be shorter than I thought it was going to be. And then return U. Right? Okay. I'm just going to take this into a new chat and get it to generate some tests for me. Hopefully it'll be correct. New, oh, sorry, not search chats, new chat. I didn't even know you could search chats. Oh well. Command V. Give me asserts to check the output of this. I didn't use NumPy arrays, just regular Python lists. The output is a list of lists with each sublist being the basis, being a orthonormalized vector, being a basis. Okay, orthonormalized vector. The reason I'm just like giving that description of like with each sublist being, first of all, because like the task itself was to actually do this with NumPy arrays. I just once again gave that challenge thing and wanted to do it just with the regular lists. Ask questions, fix bugs, generate PR. Codex can do it all. Alright, Codex. ChatGPT's trying to sell me stuff. Grok 4 is making waves. AI is getting out of control. Anyways, the reason I described this because in my head I see like many different ways to actually return the output of this, right? Okay. Actually, give me the vectors so I can check. Because it just gave me the framework for writing the tests. It didn't actually give me some test vectors. let's just do this. This looks convincing enough. Hopefully it's accurate. Orthonormal basis, original vectors. Okay, so the length is fine. I don't understand what this means. Okay. So I think that's if the orthonormal vectors are correct, which I think they are. Now we do this, and we'll set orthonormal basis as GS orthonorm original vectors. I think I haven't run the cell yet, so I'm just gonna run that. Let's see what happens. And yep, something broke. Let's see. List object cannot be interpreted as an integer. Okay. Get some vec p, so it breaks at get some vec p. So I did something wrong in some vec p. Let's see what the issue is. Okay. Project, no, project is the vector itself. So for I in read 1 comma vex, yeah, the issue seems to crap out at get some vex. Getting the sum of the vectors. What have I done here? I give it a list of vectors. Yes. Okay. P is a list of vectors. Right. And then I take the first value and I put it to this, and then some vex. Oh, I see what the issue is. No, that's fine. Some vex is just the first element, and then starting from the second element, I just take that second element, add it to itself, and set some vex to itself, which makes sense. So maybe there's an issue here. I take two vectors, enumerate over the second one, a idx plus n underscore b, get that list, and return it. And that's the new sum vex. And then I return that. Okay, I don't understand what the problem is. Who's asking? Oh, I see what the problem is. I'm a silly person. I am a silly person. Range len vex. There you go. Let's see what happens here. Oh crap, I passed all the asserts. Nice. Let's see what these asserts are about. So asserting that the length of both is the same. Okay, that part, this makes sense. To verify, each vector has unit length. Okay. For IDXV in enumerate orthonormal basis, norm equals sum squared for x and v. Okay. Assert that this is less than the tall, and the tall is 1 unit 6. So basically assert that norm the norm squared, right, which is the L, isn't that the L2 norm? No, the L2 norm raises square roots it, right? So why is it just norm SQ? I get what it's saying. For I comma v, I greater than equal to j, continue, equals sum xy for x comma y and zip vw, assert abs dot product less than tolerance half dot product not equal 0. Right? And I think that makes sense, right? When should be approximately off diagonal and 1 on diagonal. So basically the dot product with itself will always be 1, and the dot product with something else that's not itself is 0, right? This should be not equal to 0, so that's what this is testing. So it seems to be correct, but, and the dot product part is fine. I'm having a little bit of trouble parsing this loop, because zip, if I remember correctly, it, anyways, I'll look over this later, but I think we got what we needed here. So I'm gonna go over this and do like a proper like lesson style video tomorrow, and put this all together. And I'm gonna try and also in that video like go over the code here a little bit, like just like a little bit. This part is fine. It was not completely fine because I'm like, wait, check orthonormality via dot products, right? Oh, norm squared. Okay, so this is just the dot product of the thing with itself, right? That's why it's 1. Got it. My bad. Should be 0 off diagonal and 1 on the diagonal, and this is checking it on the diagonal, which is fine, right? Because it's just checking. Being on the diagonal means it's with itself, right? So I think there was a thing here that explained that. I had asked a follow-up question that made sense, and it explained gram matrices to me. There you go. Which produce our orthonormal vectors. The quickest way to check that they really are orthogonal and unilength is to form all their pairwise dot products, right? Where this matrix Gij is essentially the dot products of, where each element in the matrix G is the dot product of the basis vector I with the basis vector J for all for I starting from 0 through 1 and J starting from just 0 through, not 0 through 1, 0 through n, and J 0 through n as well, right? And diagonal entries, aka where the I equals J, aka where you're taking the dot product of the basis vector with itself. And you should get 1, and off diagonal entries you should get 0, because you know if they're orthogonal it'll be perfectly misaligned. Actually, now that I think about it, I mean, this intuitively makes sense to me, and I've heard this before. I'm just gonna Google why orthogonal leads to dot product 0. The dot product of two vectors is calculated as the product of their magnitudes and the cosine of the angle between them. The dot product of two vectors is calculated as the product of their magnitudes and the cosine of the angle between them. Well, that's one way to do the dot product. And then it's the cosine of the two angles. Let me look at this image here, because it's actually pretty good about spitting out images that make sense. These are orthogonal. X minus y. What is this? These are just two different. This is the algebraic definition, and there's the geometric definition. So cosine of 90 is 0, if I remember correctly, which is why this is 0. How does it work out in the algebraic definition? I mean, I believe it. I believe that they're equivalent definitions in some way. Yeah, length in 3D, length squared in x dimensions. Ooh, Pythagorean theorem in n dimensions, okay. We can say okay. Is the magnitude of x squared length squared, so magnitude squared, so you take the L2 norm and then square it again, you just get those things squared up and added, which is essentially just the dot product with itself. Okay. Using that with the Pythagorean theorems, xy. Okay. -2. Why is this 0? That's the part that doesn't make sense to me. Geometrically, being perpendicular makes sense because cosine 90 is 0. Let me just confirm that. Cosine 90 degrees. And it's got to be 90 degrees because it's orthogonal at 0. So that geometric representation makes sense. But, you know, angles and things like that, they kind of... At least I think they'd fall on other dimensions, but maybe I'm wrong. It's very possible that I'm just wrong, right? X squared was plus y squared equals this, right? Each pair. But why is this pairing of x1 minus y1? Oh, because of this. Okay. X squared plus y squared equals x minus y squared. This is the triangle inequality. How's this the a squared plus b squared equals c squared? Okay, wait, never mind. So this is playing the role of c. So it does this. And then what is, I think it's the differential. I don't understand. I think this is the differential. I think that's what's going on here. That's the only way I can see why the left-hand side goes from this to 0. This is not very much convincing me. Let's look at mathematics stack exchange. Well, this one I get, but algebraically. Well, I am curious about this. Anyways, I will look that up later. I think for now, this makes sense. Everything is working. Code seems to be in order. I think we can move on from Schmidt orthonormalization. And I think that's my time, guys. Thank you so much for this additional behind the scenes video. I hope you guys are liking it for whenever or if ever anyone ever starts looking at these things. But thank you so much. Have a great one. And, stay curious. Have a great one, guys.